still not moving from Santa Barbara. so Francesco Bullo, also from UC Santa Barbara, is going to talk about perspectives on coupled oscillators. Francesco?
Thank you, Jorge. Thank you, Fabio. Thank you, Daria, for setting up this wonderful workshop. It is really exciting and fun to be together with this esteemed crowd of colleagues and friends around the world who share the same passion for this topic. So it's really great to get together. We should do it more often, I should say. We're always writing papers and reading papers, but we should get together more often. So anyway, my connection where I'm calling from is not great, and if it breaks down, be aware that on my website you can find these slides right now, so you can download them right now as you follow my talk, and you know, there's some future directions on top of the review of recent progress that I'm going to talk about. All right, so that's one thing. I want to thank Saber Jafarpour. He's the first author on essentially all of the papers I'm going to show to you today. He's a postdoc at Georgia Tech right now. Robin De La Base, Kevin Smith, and Pedro Cisnero Velarde are also collaborators. This was the outcome of a DOE grant that supported us for a couple of years, 2016-19. Let me tell you a story today. I'll tell you a story. It looks like it has many chapters, but they're all hopefully not too complicated. First of all, I will just tell you in its simplest form what are the models that I am interested in. Elastic and flow networks on the torus. I'll call them that way. Then I'll show you some tools that we've been developing and that I've noticed very few of you are using. So I'm kind of offended by that. So I'm just kidding. Anyway, so cut set spaces and projections. I'll talk to you about the geometric theory on the torus. Very cool. And then I will reiterate what so smartly Zara talked about. I learned from her work during her PhD, the importance and value of contraction theory and how that relates to convex optimization and something monotonicity, both in maps, vector fields, as well as in this discipline called monotone operator theory. And then after that, I'll give you the main result that I want to show you today. It's about multistability. It's a recently appeared SIAM review paper, and elaborate a little bit. I am sure I'm going to run out of time. So in its simplest version, the simplest equation I could write down is this equilibrium equation here at the top. Basically, you're given some natural frequencies, and you can find an equilibrium to the system, a synchronous evolution, if there exist angles theta 1 to theta n in such a way that that balance equation comes true. And this is over a complex net or arbitrary topology. I think many of you are familiar, if not, this can be interpreted as the equilibrium of an Euler-Lagrange system, a simple kinetic plus potential energy. Here on the left, some kind of elastic energy. So there is an energetic interpretation, as it is very desirable and commonly sought for in maybe physics literature. But also, of course, as you know from power in general, there is also a power network and a flow system interpretation. So there are flows of quantity. So these two analogies are useful in what follows and what comes down. And there are Kirchhoff laws concerning preservation of quantity. So now here's a first concept here. So that was the setup. Here's a first tool. So if you have a complex network, large topology, one very important concept is, and you are hoping to understand some synchronous behavior, some flow behavior, some balance. One important concept is that of just doing a cut. If you cut your network, then there should be some balance through the cut. Very simple geometric concept. And this gives rise, this is formalized. This is a very little simple picture at the bottom right. There is a notion of cut set space and cycle space in algebraic graph theory. There's some beautiful ways of describing the spaces of cuts and writing them as vector spaces, right? This is a vector describing a specific cut. And one of the things we've been working on is developing a tool called the cut set projection operator that maps onto the space of cuts, and it does so in a properly tuned, weighted way corresponding to the topology and the admittances or weights in the coupled oscillator network. So this is a natural operator, which again, it's very rarely observed in the literature, and yet in real life it seems to be like it should play an important role. And in some of our papers we've started to understand the properties of this operator. Here I have a list. The details are completely immaterial right now, but just as an FYI, there's a beautiful concept here. It's just a tool. I'm gonna come back and use it later. So here's a second idea. So suppose you have a cycle on a graph, just 3 nodes. Let's take 3 nodes, and let's number them 1, 2, and 3. So what you do is you go from node 1 to node 2 on the shortest arc. So that's the shortest arc from 1 to 2. Then you go from 2 to 3 on the shortest arc, and then you go from 3 to 1 on the shortest arc. So when you have done that on the image on the left here, the resulting path that you have completed, I'm going to call it it's a closed path because you start at 1 and end at 1. It's composed of shortest arcs. That path wraps around 0 times, wraps around the torus 0 times. On the other hand, if you place the node number 3 at a certain location, so you go on the shortest arc, and the shortest arc, now you have wrapped around the circle once. And if you were to just relabel the nodes, you put where 2 and 3 are relabeled, now you find out that you have wrapped around -1 time if you count the number of wrappings in a counterclockwise way. So no matter how many nodes you have, no matter which cycle you select on a complex topology, there will be a number of wrappings around that cycle, right? That's called I'm going to call that the winding number. If you have multiple cycles, I will introduce a vector of winding numbers, one for each cycle. Of course, I don't want to do it for all cycles. I'm just going to use a basis of cycles, right? Okay, so I'll have a winding vector. Now, imagine you play with this node and you move it a little bit to the left and move it a little bit on the right. Notice the winding number is piecewise constant. As you move the nodes, the winding number does not change almost everywhere. Now, of course, there are positions here when this node 3 moved across the angle equal to pi, that particular antipodal position, there are jumps, right? There are discontinuities, right? Okay, so let me summarize what we have learned from this example. First of all, there is a Kirchhoff angle law. It's like a voltage law. If you go on a cycle and you sum voltage differentials, right? They sum to 0. But here, when you run around, the sum is 2 pi times k. So the Kirchhoff angle law says that the winding number is an integer, and it's upper and lower bounded by the length of the arc, the number of nodes on the cycle divided by 2 minus 1, something like that. It's not important. And here's another very important concept. If you have a continuous space and you have a way of mapping it onto the set of integers, 0 plus 1 minus 1, not the whole set of integers, just a finite subset. What that means is that some collection of points map to plus 1, some other collection of points maps to 0, and a third collection of points maps to minus 1. So this is automatically defined every time you have a continuous space, like a manifold, and you have a map that is piecewise constant onto a finite set. So this winding number induces a partition of the n torus. In other words, if you have the n torus, it's always possible to write it as the union of cells. I'll refer to them as winding cells. U is a winding vector. And those are the collection of angles on the torus such that the winding number is given to that particular specification U. So imagine we take 3 angles, theta 1, theta 2, theta 3. So now we write the 3 torus as a cube where, as you well know, the top is equal to the bottom, the right side is equal to the left side, and the front is equal to the back that you don't see, right? So it's a cube, but it's not really a cube because it's a 3 torus, right? The topology is very different. Here at the top in this image, you see visualized for you in 3 dimensions the 3 winding cells. The winding cell at 0, this is the one where, as you wrap the shortest path does not wrap around the circle or the torus, is given by this geometric shape. I hope you can visualize it, right? There are holes in it. The holes in it are the parts that I have moved to the left and to the right. To the left is the winding cell corresponding to -1, and to the right is the winding cell corresponding to +1. Again, the ingredients here are only Tn and the graph with cycles, arbitrary topology. This doesn't depend upon the dynamics. It's a geometric topological construction. So, and by the way, because I've drawn it in this weird way, I want to make the case this is a connected set. It's a connected set because this part touches the part there in the back, the top touches the bottom, and the right touches the left. So that is a connected set. And now, moreover, what's really kind of cool about it is if you remove the rotational invariance, so there is a rotational invariance in the problem, and you look at the reduced partition on the reduced set and modded out this invariance, then it turns out that these winding cells are just open convex polytopes. So here, this is the projection, open and convex polytopes. So that's going to play a very important role later. And just for fun, just because it's always good to look at fun pictures, this is, you go to 4-dimensional, there are 4 angles. I don't know how to visualize the 4 torus, but I do the reduction, I mod out the symmetry. It's 3-dimensional, and as you see here, again, I have open convex polytopes. And if you have 4 nodes, there are 2 ways of looking at cycles. One is just literally the square graph, and the other one is the square graph plus you cut it in 2. When you add this diagonal, now there are 2 cycles, and if there are 2 cycles, there are 2 winding numbers, 2 independent cycles. And so here on the right, you see that each winding, it's not a winding number, it's a winding vector. So there are little polytopes, right? Each of which corresponding to different pairs for the two cycles. So now I finished this tool. This is a geometric tool that is, I would argue, useful anytime you have n angles and a graph among them. So now let me tell you about a different tool. And I know that many of my control colleagues don't believe in this, and some of the in the audience, not everybody may be familiar with contraction theory, but it is truly a very powerful theory that I want to advertise, just like Zara did before me. So first of all, if you have a function and if you have a vector field that is the gradient of a function, or minus the gradient, I'm not going to worry about it. If you have a vector field that is the gradient, asking for the vector field to be contracting, it's exactly the same as asking for the function to be convex. And so if you agree that searching for convexity in optimization problem is an important task, well then searching for a contraction in a controls problem, in dynamical system problem, is equally important. The other thing, many of you know, a generalized version of optimization, of convex optimization, is referred to as monotone operator theory, and they're exactly the same. There is a minus sign difference between the definition of a contracting vector field and that of a monotone operator. So that's one important concept. The other important concept is that, okay, as I was mentioning to you, one should search for contraction property in doing analysis, and on top of that, one should design in such a way that the resulting closed loop system is contracting. And why would you want to do that? So here, I have a long list of advantages, and I don't have the time to elaborate on them right now. But let me just say that there are many, many desirable consequences. And let me talk to the controls people in the audience. When you speak to people who are not in controls and you describe a system that is stable, I think your audience will naturally assume that when you say your system is stable, well, then perhaps it's ISS, it has a finite gain, there is a margin of stability with respect to unmodeled dynamics, with respect to delays, and so on and so forth. So it's almost like natural properties that simple Lyapunov stability does not give you, but that if you were to establish contractivity, they come for free. Okay, so now, finally, let me come to the to the bottom line. Why do we care? So we are interested in either this, phase coupled oscillator here, and I'm looking to understand if it has stable equilibrium points, which correspond to synchronization, right? How do we do that? Well, it turns out that in each winding cell, because the winding cells are open convex polytopes, I can write the right-hand side as minus the gradient of an energy function. And the energy function has this affine term, so typically this is not possible to be done on the entire N torus, but it is possible to be done if you restrict your attention to one specific cell at a time. Because in each cell, the angular differences are less than pi, and so you're going to be fine. Now, because that's an affine term, the Hessian of the energy is easy to compute, and the linear term does not appear. This nonlinear term is well known, widely studied, sometimes called the spacing potential. It's well known, its Jacobian is equal to minus a Laplacian matrix with weights that depend upon the angle. If you restrict your attention to angles that are pairwise less than pi over 2, all of those cosines end up having a positive sign. And the bottom line is that you have a strongly convex function and you're looking at the gradient of it, which means it is strongly contracting. And so now you have a strongly contracting vector field on each of these winding cells. I never said, and it's not true, that the cells are forward invariant. So what is true is that if in each cell, if you remain in the cell, there has to be one equilibrium. If there is no equilibrium from all initial conditions in the cell, you will leave the cell. So this is an at most uniqueness result. On each cell, there is at most one equilibrium with this cohesive property of having angles upper bounded by pi over 2. Now, there's piece of codes out there that will, given a graph, will compute simple cycles for you. And from the simple cycles, you compute the winding cell. And then you can write an algorithm, a contraction algorithm, that studies each individual winding cells and determines if a point exists or not. And that's the best possible algorithm you may get to in terms of computing all stable synchronous evolution of this system here, or cohesive synchronous evolution of that system there. So it's a wonderful construction, and if you put everything together, things work out. So I just wanted to add one more picture. This is the same picture as before, but I'm looking at the subsets of the cohesive cells where I focus on the cohesive subset, where each pairwise angular difference is less than pi over 2. In power system application, that is critically important. I believe power systems are never operated outside of this range. But it certainly is an open problem, as I will show you, discuss briefly later. We don't really know very well what happens in the open regions. When you are outside of the cohesive cell, you end up with a Laplacian that is signed. It has, or a graph that has edge weights which are positive or negative. And so there's a nascent theory of signed interactions. Beautiful results, no time to talk about them right now. Perhaps they're relevant to understand all equilibria of these models. Now, let me, for example, mention the work of Robin. So imagine you have losses, just like Jürgen was talking about earlier today. Now, if you have losses, the dynamics is perturbed. But if it is a perturbed dynamics, if I have a strongly contracting map, and I sum to it a perturbation, the result is strongly contracting under some boundedness assumption. So the contraction rate has to overcome the Lipschitz constants of the perturbation. So you get an immediate robustness results out of that. And of course, then one can go design an algorithm, and there's a wonderful paper by Robin and Saber that you can read if you're interested in. But the key point is that, hey, I got automatic robustness out of the contractivity. So the next question you may ask, and Fabio, maybe I can ask you how many minutes I still have, is the next question I have is, how do I check if an equilibrium exists or not in the cell, in each of the cells? And there are two approaches to doing that, and let me come back after a very simple rewriting. That equilibrium equation ends up being determined uniquely by that cut-set projection operator that I was discussing. And this is an inverse problem, and you can solve the inverse problem using a power series expansion that reminds the power series expansion for the sinusoidal function. And here I have, an illustration of how accurate you can get as you increase the order of the approximation. Years ago with Florian, we had a PNAS paper where essentially we were using just the first order term, and now we have a much better understanding of all of the higher order terms, leading to more accurate approximations and understanding of this. And then finally, but in terms of not talking about series expansion, but just talking in terms of the synchronization threshold, as Igor was talking about earlier, I want to understand exactly when does the system synchronize as a function of the parameter. So you can do two things. You can define the induced norm of the projection operator, the cut-set projection operator, or you can define, and here this is ununderstandable, but the details are omitted, something called the minimum amplification factor. And on a real axis, if you put 0, alpha of p is of course smaller than the induced norm of p. And basically the theorem tells you that if your power injection or natural frequency heterogeneity, it's in the vector z, is in this range, then a solution always exists. And if it is in that range, the solution never exists. And unfortunately, in the literature, there remains a gap in understanding the necessary and sufficient conditions for synchronization. You can obtain that exact value through the series expansion I showed you, but other than that, these are necessary and sufficient conditions. But there is necessary conditions and sufficient conditions, not both properties at the same time. All right, I just want to, we talked about the importance of data. Another thing I want to talk about is the importance of benchmarks. One of the, when you try to understand synchronization, right, we want to understand this threshold. These are state-of-the-art results on various IEEE test cases. So these are, power systems example codified by IEEE. And essentially the first column was how close we get to predicting the exact value. And when we get to 0.1% of the exact value, that means that we are 3 orders of magnitude away from the exact value. So old available tests were terrible when you were looking at models of with 2,400 nodes already. This was 0.1% accuracy. And with the results that I've shown to you today, Saber was able to push this accuracy to rigorously to 29%, and approximately by means of numerics approximations to 80%. So we are making progress. There still is a gap between necessary and sufficient conditions, but we are, and I think we need the help of somebody expert with non-convex optimization, because we have numerical evidence that if we could solve those non-convex optimization problems, we'd be able to get really accurate results. And I apologize, I didn't say what the computation of the minimum amplification factor is non-convex, whereas of course the induced norm is not only convex but very elementary problem. So how much time do I have? I apologize.
A few more minutes, just
a few more minutes.
5 minutes.
All right,
yeah.
Perfect. So I think my story is almost over. There is an entire parallel story, but I knew that Zara was going to do an amazing job, much more complete than I could. So this next slide is really the same sets of ideas that Zara described. It's related to the concept that so far I've showed phase-coupled oscillators. But of course, many realistic systems are described in the state space, and one really should try to study state space oscillators. And what Zara showed, an equivalent language for it is using the concept of semi-contractional theory. You're still using contractional theory. But you're not looking at the norm on the entire state. You're looking at pairwise differences going to 0. Essentially, the results that Saber and I have in this area have to do just like the question I asked Zara, which is what happens when you use norms that are non-Euclidean. So a long story has to do with trying to understand what is the right norm to use to study contractivity. It really is the same question as what is the right Lyapunov function to design. There are, of course, in control theory, there are very many different Lyapunov functions one may design. There are some classes of systems are better suited for L1 or L infinity norms compared with L2 perhaps. And so here we have a result which works with respect to arbitrary norms, and we're very happy with that, and it should be combined with analysis of identical coupled oscillators subject to noise that Zara showed. Okay, so this is the end of my story. Once again, let me summarize it. I have started with a very, very simple model. And you should complain to me because I really would like to understand much more complicated model with heterogeneous dynamics, with exhibiting richer behavior and so on and so forth. But this was just my excuse to show you some tools which I think are helpful in looking at this more complex problem. The cat-set space, the winding partition, contraction theory, convexity, monotone operator, and then I showed you some example results in terms of multistability, in terms of getting to the exact value through series expansions, or at this moment in time the gap between necessary and sufficient conditions. So let me take 2 more minutes, or at least until Jorge stops me, to just briefly mention some open problems that later on we'll discuss. Before I forget, all of these papers are available online right now, and you can find the slides on my website, so you can follow the links and download them. So I see problems in fundamental theories of phase couple and state space oscillators. I see lots of problems. Many of us talked about energy systems, and later on I'd like to talk to you about machine learning and scientific computing, which is a topic this community has not worked so much about. Anyway, lots of interesting cluster synchronization. I already talked about sine graphs. Also non-monotonic couplings are interesting. I think there's a lot of interest in really understanding cluster synchronization and bifurcation diagrams, such as the one illustrated here. Recently, contraction theory has been developed to understand fractal attractors, and transverse contraction holds the hope to give us extremely sharp conditions that we would be able to use in benchmarks. You're all familiar with multistability, so I'm going to skip that, and I'm going to come back to that later. Maybe let me just talk about this conjecture that Robin elaborated. I've shown to you multistability in coupled oscillators, where, if you think of them as power systems, there is only the angle dynamics. This is an example where even if you introduce the voltage dynamics, then high voltage solutions are characterized as living in a thick torus on the complex plane, and our conjecture is that the utmost uniqueness result holds also for the active reactive power flow equation, perhaps also for optimal power flow, if you generalize this notion of winding cell in the proper way. And it's very important to understand these winding cells. There's all sorts of counterintuitive paradoxical behavior that you can observe. For example, you would imagine that losses are undesirable in general, and yet there are cases in which losses increase the power flow capacity of a given network under given conditions. Very interesting. And I'm out of time, right, Jorge? I am out of time. So I will wait for my time later on to talk to you about machine learning, scientific computing. Thank you.
Great, thank you. This was great. We'll have some time later in the discussion. For this. So any question or comment for Francesco?
I have a quick question, maybe. So what's the complexity of computing the winding number and the partition? Because it seems to depend on the number of cycles in a network, and the number of cycles grows, I don't know the rate.
Yeah, it's exponential. The number of winding cells in general grows exponentially with the graph. However, there are graphs for which you can. So, for example, if I give you a planar graph, and there's a natural choice of cycle bases, and if the cycles are too short, then I can quickly tell you, there maybe exists only one winding cell. So the analysis of the basis of simple cycles is, and now that's graph theory, pure and simple, is what determines this exponential growth that you're mentioning.
Okay. And is there a relation between the size of the cells and the possibility of having an equilibrium?
Yeah, of course. Yes, yes. Thank you, Fabio. I gave you a bound earlier. So the number of nodes divided by 2 minus 1 is the largest winding number you get. So if I give you 4 nodes, or if I give you 3 nodes, then the winding cell is the cohesive winding cell will be only 1.
Okay.
You need to have many nodes in order to make this happen.
Okay. Thank you.
Thank you, Fabio.
Arvendo, quick question or comment, and then we'll move on.
Yeah, whether the semi-contraction sufficient condition is local or global stability condition?
The contractivity conditions, well, it depends upon the condition. If the system may be globally contracting, like some of the state space oscillators that I briefly showed, that Zara showed. The case of the phase-coupled oscillators, inside each winding cell, each phase-cohesive winding cell, it is contracting, but not globally. It's like having an energy landscape that has multiple minima. In a neighborhood of each minima, you have good behavior, but globally, of course, not. Thank you.
Great. Excellent. Thanks a lot.